As promised in the previous segment, this segment will be about all the connections or connectors which will be used to join basically different bodies to make a complex system. And then this is, I think, one of the very important chapters or segments, because they will allow you to draw free body diagrams, because without them you can't draw proper free body diagram. And if you draw proper free body diagram, then any problem can be solved very easily. So that's the whole thing. Okay. So we are going to talk about in how many ways generally mechanical systems use connectors to connect different bodies to make a whole system. And then the forces will come, external forces, loadings, all those things are separate, but this is just the creation of the physical system on which the loads will be applied. Now one of the, okay, let me start with this. So number one, this is a sort of a rope or thread or something. Suppose you have some block like that and here you are using a thread or rope to connect, okay, this point to the ground maybe. Okay. Now, and in such situation you might have seen, for example, the cables which go through the bridges, the electric wire, the poles, electric poles when they are connected, all those flexible things where the length is so much and the mass per unit length is they are very slender, so that they are flexible. And there are two cases. So I was just about to say that either you can neglect the mass or you may not neglect the mass. It depends on the situation and the accuracy at which you are working, plus the material and the thickness, all those things. Okay, only being flexible doesn't mean that you can always neglect the mass, but there are cases when you can neglect the mass. The point is, if you have such a thing and then you draw the free body diagram of this block, okay, we are not interested in the free body diagram of the rope or the cable, but of this. Now here, so if you, now the ground, in fact, let me do one thing. So let's not even say that it is connected to the ground, because then again some more forces will be needed to be shown there. So I don't want to make it clumsy. So let's assume that whatever is there. So this is just a unseen part of this body. Now the point is, what when you are taking away this body to create the free body diagram. So suppose this is the, sorry, so you are trying to draw the free body diagram of this block. Then you have detached this string, but then you have to replace this with the force which it was earlier exerting on the block, and that you should show maybe something like this. Suppose it was in tension, and then a flexible rope or a cable or a thread or something, it cannot exert any compressive load. That is the meaning of flexibility. Okay, so it cannot. So always this force has to be in this direction. Now if you can always put this and then the answer will come to be negative, but generally you should use some engineering sense always to keep it as proper as possible. And in some cases anyway there will be no way in which you can actually decide about the direction, but in this case obviously the direction can be known a priori. In fact, again, I am talking about the sense, not the direction. So, direction I will come to that in a moment. Okay. The sense is in this way because it is a tensile load. Now, so this is talking about the magnitude of the force, but then what about the angle which this thread will make? Now, if the geometry is given and it is told that it's massless or gravity is neglected something, then directly from this geometry you can get this angle theta, wherever this angle theta is. So, you can create that angle theta. Okay. If say suppose this is your y direction or something, so with y direction it will be theta. But it may so happen that you cannot neglect the weight of the cable, then the actual shape of the cable will become something like this maybe, okay, and this shape this shape is not known a priori because it depends on so many things, the angle of inclination of basically the angle between the point A and point B where it is connected, mass per unit length, and so on those things it will depend. So, you do not know the exact shape, that means you do not know the exact tangent at this location, that means even you do not know the exact theta. So, in that case even the theta will become an unknown. So, you have to be very careful while reading a problem to understand and to ascertain that whether you know both direction and magnitude, you know only magnitude and do not know direction, or you do not know the magnitude but know the direction. Okay. So, these are the things which are very important. Mostly what happens is, if the question will ask you about what is the tension in the thread. So, that means it is asking about the magnitude of that force, but then you have to be very careful to think about whether you know the theta or not, depending on whether the mass is neglected or not. Yeah. So, that is one point or one type of connector. So, the connector here is the flexible cable, thread or rope. Then coming to the second connector, it is two smooth surfaces in contact. Okay. Suppose this is one surface and this is another surface. Okay. Now, here the connection between them, now as opposed to this, here we do not have a very physically visible connector. Here we were saying that a thread is the connector. Here this surface, two surfaces are the connectors, or you can say that both of them are connectors, part of the connectors. Now, so here if friction is absent, if frictionless, if the situation is frictionless, then suppose you are drawing the free body diagram of this green part, okay. Then so let me draw like that. Then you are removing this green body out of this system. So that means you will have to replace this body, this orange body, with the force which it was exerting, okay. So now the force which you will have to replace it with will be normal to this, okay. So that will be normal to, so how to show that, so if it is the tangent, so it is bad drawing. So if it is the tangent to that surface, so this force will be normal to that tangent. So that is the meaning of that is the way in which you should replace the force when you remove this body and draw the free body diagram of this. Okay. But then if this is not without friction but with friction, so mu is not equal to 0, then what? Then the situation will just change to here it was like this, and suppose I still again I'll draw this tangent. Okay, this is bad. Okay, so this is the tangent. Now this force, now the F which will come, it will not be normal to that but in some angle. I will not say n now because it is not the normal force, but the thing is there will be some force which will act at some angle. Now earlier only the magnitude was of Fn in a way was not known. Okay. So what was not known was the magnitude, but now even the theta is not known. So when I am saying not known, I should say that okay, these are the variables which you should be careful about, because depending on the problem something will be known, something will be not known. But when I am saying it is not known, what I mean is that you should be very careful about while thinking about them. You have to ask yourself a question, do I know this angle by some means? Okay. And in problems when you read it properly, many times one of them will be known if you do a little bit of thinking on that. Okay. So point is you think about them. Yeah. Then what? Okay. So these are two things done. Let me go to the third one. Say third case. This is called the roller support. Okay. Now this can come in many forms. For example, you have let me draw the ground with something like this. Say, suppose this is the ground. It doesn't look clearly, you can't see it. Say this is the ground, suppose. Okay. And on that you have something like this. Okay. And maybe this has got some something like that, and there is a pin joint over here. Now okay, let me do even this, sorry, that to show that this is the ground. And now suppose this is the roller support which you are talking about as a connector. Then what now suppose if you are trying to draw the free body diagram of that orange bar. Okay. So when you are trying to draw the free body diagram of that orange bar, now where do you apply the force to replace this whole thing? Means you are trying to detach this bar from the system, that means from the ground. So now this is the connector. Okay. This roller support is the connector which you want to remove. Basically you want to detach from the ground by removing the connector also, and thereby you are basically trying to replace whole this connector plus ground with the force which was getting transmitted from the ground through the connector on the body. Now that will come as like this. Okay. Perpendicular to this surface on which it was rolling. Now that's a very important thing to observe, that because students generally think that this force will come in the direction of the bar or something. So sometimes they get confused about that, but please make sure that this again it's like the previous point which we discussed, right? So here the point of contacts are like frictionless. Whenever this roller support is given, you have to almost always assume that it is frictionless, very rarely it will be mentioned that there is friction in the roller. Okay, otherwise you will have to assume that it's frictionless, and then when it is frictionless, the force will just be coming upwards. Okay, so that's how you will have to show the reaction when you, or a force when you remove this connector. Just here one point I wanted to make in the previous, I just remember now. When I talked about this force, and when you don't know the angle theta, there are two ways to see this. One is this, the way I said, a magnitude and a direction. The other one is, what should I, maybe yellow, yeah. So, another way to look at that is, you are having one force in this direction and another force in this. Okay. So, basically you can say this, or you are habituated to call this as normal force and this as the frictional force. Okay. So if you remember the representations of the vector, basically this is in a way, means what do I call, magnitude unit vector representation sort of thing, where you know the angle and the magnitude. And here this is a component representation of the vector, of the same vector, the force, total reaction. So please note that this is normal reaction and this is total reaction. So the total reaction, which is a physical quantity, so immaterial, it does not depend on in what way you represent it. So that total reaction, you can represent it as a unit vector form or in the component form, and you are quite acquainted with this component form, and you call that a normal reaction and a frictional force. Okay. But we will see that once we go ahead, you will notice that this form, the unit vector form, again will be much more useful and handy in solving many problems rather than using this. We will come to them. Okay. Yeah. So now coming back to this roller support, I just wanted to say that if friction, if you consider friction there, then again this will not remain like that, and a force in a random direction will come depending on the friction and all. Okay. But in roller support, 99.9% case you will not see friction's existence. But more important thing is it comes in many types of representations and views. So that is more important to see. Suppose I draw another case where this is the ground and you represent the connector like this. Okay. Say there are some rollers and on that something is here, and over that you are connecting this thing. Okay. And maybe, yeah, dotted line I can show here. So this again is the same thing. So for this also, the orange color block, if you want to remove as a free body, the force will just be like this. And say one more example, if I want to give, this is the ground, and say you have, what color am I using? Yeah, so say something like this. Okay, so something like that you have kept on the ground, and then again you have connected this block. Okay, so all these things are different types of, these are not the only types of roller supports, but some representative types which I have shown here, so that any of these kind of things when you see in a picture which represents the actual physical condition, then you will have to replace the free body diagram with this force. Okay. Okay. Now coming to number 4. let's say number 4. This deals with a sliding guide. Okay, let me try to draw something like this. So suppose there is a guide like this, a sort of rod which is very smooth, and where it's connected, say, to the ground like that. But over that you have put some say slide like that, and then let me do one thing. So these are dotted lines, so that this is behind this in a way. Okay. Okay. Now, so that means, see here, this block can freely slide on that rod, smooth rod. Okay, and then on that, what you have done is you have created a, suppose now here, sorry, I'll again remove this much. Okay, so now that one is actually is free to move on that, and then whatever angle it is there, suppose some 70-degree angle it is making with this orange block, and the orange block is free to slide on this green colored rod. Okay, but then if you are trying to draw the free body diagram of this bar, so what you have to do is, let me draw it here. Say suppose you are trying to draw the free body diagram of the bar, then you will have to show the force like this. Okay, so that is a very important connector, the freely sliding connector with this, and then it doesn't depend on the angle at which students they make this mistake a lot of times, that they try to feel that the force will come in this direction. No, it doesn't. In the free body diagram you have to show the picture like this. Maybe the component in this direction will do something special, which we will come to in, I think, the next segment, but when you show the free body diagram it will have to be like this. Okay, and then what, yeah, then one of the very important joints, that's called the pin joint. In fact, before even defining it or discussing it, we have used it, like in all the pictures, assuming that intuitively all of you have seen a pin connecting two things. Okay, but the actual connections are more elaborate than just a pin. It could be even a very sophisticated roller bearing, and okay, so then but the schematic representation is shown something like this. I always have been drawing it like that, and say this is your bar, okay, and here it's the pin. But then if you try to draw the free body here, okay, free body of the bar, and you want to detach it from the ground, so this is the connector here. So here this orange color is the connector, which was connecting the bar to the ground. Here this is the pin joint, is the connector which is connecting this orange to the ground. Now when you remove this, you will have to show the force not perpendicular like this, but at some angle like F. This is the total reaction type. The reaction from the pin joint will be at some arbitrary angle, and in a way again you have to think about the magnitude and the angle both as, you know, unknown quantities. You have to think if something is known by some other means. Okay? And this is one way of seeing that. Another way to see that is in a component wise again. Okay, so suppose this is x direction and this is the y direction. So f y and fx you can think of or F as a unit vector form you can think of. So where you will say that this F is F hat which will define this angle basically, and times F's magnitude. Okay, so like that. So whenever you see a pin joint, you can think of these kind of two things, and then again students always feel very compelled to think that this F will be in this direction. No, it will not be, not necessarily be. So it could be at some other angle, and this force can be at a completely different angle. Okay, so that should be very clearly kept in your minds. Okay. Then comes, say, another important joint, which is called the I think the sixth point. It is the fixed support. Okay, that means you suppose you have a wall or something like that, and it's completely inbuilt into something like this. Okay, so this is completely a rigid wall. Now here, if something is like, and many times in the schematic it is not drawn that elaborately, and you just see that something like this is shown. So these two drawings are equivalent, and I have always been calling this a cantilever beam, like that. Okay. Now here, when you draw the free body diagram, now you have to draw something like this. Suppose this you have detached from the ground. Okay, the connector was this portion which is holding the thing. If you remove that, you have to replace that ground with a force. Now that you should replace that with a force, say F, and a couple, say C. Okay. So both a force and a couple will be required. This force, okay, one more thing. Sorry, this is the color I use. No? So this force need not be only in the vertical direction. In fact, you should show both. I should draw it in different color also. Maybe this. So this one. So I'll call this F vertical. Then F horizontal, and the couple. Now these are the three things you should replace this full thing with when you try to draw the free body diagram like this. Okay. So then this is one of the very important connectors, the ends, which you will encounter in many of the problems. So please do not forget to include both FB and FH and C. And one more important point, which I must say, that in free body diagram you never should calculate something to remove something. Suppose you are able to calculate from that drawing or the situation that the force will come out to be 0, but then please do not remove that from the FBD, it will be wrong. Whatever can come, you should draw that. If it has to be 0, it will become 0 at the end, but please do not remove it from the FBD from the beginning. You keep it, means if there is a possibility of a force coming there, you show it on the FBD. So this is the crux of FBD. So these are the major 6 types of connectors which will almost cater to all the problems which you are going to solve, and there are some other small little important things which we will discuss as and when some problems require that. With that, basically the FBDs and the connector thing is over. So we will now use these concepts to solve some problems, and that is the only way to, in fact, get acquainted with the FBDs, the reaction forces which come from what kind of supports, and that will be the example part, and then later on we will get into the large number of connected bodies, that is the plane trusses and frames and everything. Okay. So see you in the next segment then.